Here we go. We got a little challenge problem for you here, okay? Goes as follows. We have a 5-meter board. It weighs 215 newtons. It's attached to the wall by a hinge. There's a hinge here. Let's go ahead and label that right here. This is the hinge. Actually, I'll zoom in so it's easier to see. There we go. And the hinge can pivot. So that's important. You always have to identify a pivot point, because then you can figure out which way torques will be applied there, okay? So the pivot is right on the wall there. Let's continue breaking down the problem here. So it can rotate vertically. Its far end is supported by a wire. Here's my wire here in the blue. I'll make this blue. That exerts a tension at an angle of 60 degrees with the horizontal. A 600 Newton person is standing 1.5 meters from the wall. So they're standing right here on the board. And the challenge is find the tension in the wire, okay? So most people would be like, this is weird. Why would you ever do that, okay? So a simple example is hanging up a sign, or you have a scaffolding that people stand on, like if they're painting a house or doing construction. So if you recall, we had looked at a problem where we looked at forces in equilibrium. If you hang a sign from a pivot point and then you have like a cable, or in this case a bar holding it up, all the forces have to balance out. The forces in the x direction balance out the forces in the y direction so that this thing doesn't snap the hinge here, fall down, kill somebody or whatever. And now we're making it more complicated because we're putting a person on top here, okay? But in real life, you probably have a big scaffold where people are painting or fixing like the side of a building, etc. there, okay? Or maybe in this case, we got a little leprechaun sitting here there, okay, to get more business on St. Patty's Day there. So anyhow, this is what the problem looks like basically here, okay? What's hard is, in the end, it's not the math, it's just visualizing all of the forces and the torques here. Big idea for this unit. In the last unit, it was all about energy there, right? The energy initial is equal to the energy what? Final, okay? In this case, it's the torques that have to balance out, okay? So torque, quick little review here, is equal to force times distance, okay? But it's the force that's perpendicular to the distance of the pivot point there that matters there, okay? So in this case, here's the big idea. The big idea is that the torques in the clockwise direction have to balance out the torques in the counterclockwise direction. What do I mean by that? If you think about a clock, 12 o'clock is up here, 3 o'clock, 6 o'clock, 9 o'clock, okay? You can either twist something to the right, this is in the clockwise direction, or you can twist it to the left, this is counterclockwise. Or if you're British, I think they say anti-clockwise sometimes, okay? So how's this going to help us? Real simple here, okay? All we got to do is we take our board and we look at, from the pivot point, we work our way left to right, okay? Left to right to see if it's creating a clockwise torque or a counterclockwise torque, okay? So let's start at the pivot point right here. The first force that's trying to twist the board, one way or another, is the wall, okay? The wall is actually pushing upwards and to the right there, yeah? But in this case, because the pivot point is right where the wall is pushing, it doesn't create a torque because it's right on the pivot point. The distance is 0, okay? So one little trick is when you pick your pivot point, in this case they gave us a pivot point, but later on they might not give you a pivot point, you can pick wherever you want to be your pivot point. Usually you can pick one where there's an unknown and it'll drop out because the distance is 0. Now, if you think about it, right, when you're trying to put a screw into the wall there, okay, the only force that matters, okay, is a force that's perpendicular away from the pivot point there. If you push straight down, you're not going to really twist the screw in. You'd be trying to shove it in, right? So you always want to maximize your force perpendicular to the pivot point as far as possible there. So now we're going to work our way from left to right to look at the clockwise torques versus the counterclockwise torques. So the first force is right here from the person, okay? And the person's weight is pushing down in the clockwise direction. How can we find this person's torque? It's just the force perpendicular, their weight of 600 newtons, applied at a distance of 1.5 meters from the pivot point. We're not going to worry about units till the very end there, okay? And the units for torque, you can already tell, is how many newtons per meter you're applying there. So in fact, if one of your relatives or your parents are really into working on cars and things like that, they might actually have a torque wrench, and it'll actually have Newton meters or pounds inch, okay, of torques that you're applying. Or foot-pounds is another common one there, okay? So we have 600 times 1.5 meters for the torque in the clockwise direction applied by the person. What's the next force that's being applied? Right there in the middle, right? Okay? This is right at the center of gravity of this board at 2.5 meters. This is 2.5 meters from the end of the wall there. Okay? That's where it's going to balance out. That's the weight of the board. So our next clockwise torque would be 215 newtons times 2.5 meters. Okay? Finally, how come this board doesn't fall? What's holding it up? The string, right? The string is holding it up. And the string is doing two things. Here's what's tricky, okay? The string is actually pulling up perpendicular. That's what counts, okay? Tension perpendicular. And then it's pulling it into the wall. Or you know what? Maybe I'll do it in the y direction. That'll be easier, okay? Tension in the y direction, tension in the x direction. But the tension in the x direction is along the axis of rotation. Therefore, it doesn't create a torque. You see that? It's only the tension in the y direction that's perpendicular that's creating that twisting force. Make sense? Okay? So why is that important? Here's what's important. It's only the y component of tension that creates torque. If this is a 60-degree angle in here, this is also 60 degrees. If this is a right triangle, this is a hypotenuse. To find the opposite side, the y component, this is going to be t times the sine of 60 degrees is what's going on. Okay? I need a little bit more room here. I'm going to slide this down there. Okay? It's t times the sine of 60 degrees is the key there. So in other words, we just found the torque in the clockwise direction. The torque in the counterclockwise direction is simply equal to the force, which is t in the y direction, times the distance from the pivot point, which is 5 meters. Okay? So now, it's not that bad. We just did the hardest part, which was setting up all of the torques in the clockwise direction equal to the counterclockwise direction. Now it's simple algebra. It's going to be plug and chug. Okay? On the left-hand side, if we get out our calculators, let's go ahead and plug and chug here. I'm going to take 600 newtons times 1.5 meters, add to that 215 newtons times 2.5 meters, and I get a total torque of 1,437.5, 1437.5. And the units are newtons times meters of clockwise torque, okay? Trying to pull this board down in the clockwise direction, twisting it about the pivot point this way and this way. It's a way to picture it there, okay? And then counteracting that is this string, this tension in the y direction, trying to twist it up this way in the counterclockwise direction, okay? Maybe too many arrows. Let me just clean that up a little bit there. Just trying to get you guys to picture that there, okay? So in the vertical direction, in the counterclockwise direction, we have tension in the y direction, which is t times the sine of 60 times 5, okay? So how can we get t by itself? Real simple. We're going to take 1437.5, get rid of the 5 by dividing out 5 from both sides, and then we can divide out the sine of 60, okay? And then we're done. The only tricky thing is make sure you're not in radians when you do the calculation. Hit the mode button. Make sure you have degrees selected. Okay? That's a common mistake. When you go back to math, switch back to radians. And when we're done, we get a tension of 331.976. So let's just round that off to 331.98. Good enough. Okay? So in other words, what do we just solve for? We just figured out the tension in the wire that's necessary to support this beam with the person sitting on there. Okay? In real life, once you know that minimum tension, you would just pick something a lot stronger for this, this bar or this cable to hold it up. Okay? So if I knew that this had to be 331.98, I'd probably pick a bar that could hold 500 or 600 newtons just to be safe.